In this video, we're going to talk about rational expressions. In particular, our goal is to reduce rational expressions. But before we get there, let's discuss what a rational expression is and kind of introduce this concept. So, a rational expression is a quotient of polynomials. And here's an example: a squared plus 7 over a minus 4. And I just want to remind you of what a polynomial is. So, a polynomial is the sum of multiple terms. So poly means multiple, and terms, our book defines terms as being the product of numbers and variables. Numbers and variables. So an example of a term could be like 3x. That could be a term. All right. But a polynomial would be the sum of multiple terms, like 3x squared plus 4. That's a polynomial. Okay. So that's the idea. And we're looking at quotients of these. I know if you might recall, a quotient is the division between two polynomials. Sum, of course, is the addition, and then product means multiplication. Lots of math words in just a few statements there. Okay, so there we go. That's a rational expression. And what makes a rational expression kind of important is that really we have variables in the denominator. And that's an important distinction because we don't really consider something like, let me write it in a different color, 3x over 7. That's not really considered a rational expression because there's no fraction, I'm sorry, no variable in the denominator of that fraction. Okay, so let's go ahead and work with this. Before I do that, we need to talk about one more concept, and that's domain. We're going to revisit this in a later chapter, but for right now, domain is the values we're allowed to plug in. Values we can plug in into our variable. We often think of this concept as input. And I apologize for my voice. It's a little bit weak. So let's look at this example that we had up here of a rational expression. Let's talk about the domain of it. So really what we're interested in is what we can't plug in. So you notice how they asked for the excluded values from the domain, what we're not allowed to plug into our variable. And when we're working with a fraction, we have to be worried about the denominator not equaling 0. So we do not want the denominator to equal 0. So that's what we're going to do then, is see where the denominator equals 0. And I could look at this and I'm like, okay, well, the denominator is a minus 4. And that thing is going to equal 0 when a equals 4. So like I kind of create like a little solving equation here. And I get that a can't be 4. So that would be what's excluded from this. 4 would be excluded from this domain. I could plug in anything but 4. 4 is going to give me 0 in the denominator, and that is a problem because I can't divide by 0. All right, so let's look at a more exciting example. In this denominator, I have something more complicated. And in fact, when we see something that we can possibly factor, we're going to factor it. It's going to make our life a little bit easier. So I'm going to rewrite this as x minus 9 over x plus 5 times x minus 5, because that's a difference of squares. And since I'm interested in where the denominator equals 0, I'm going to go ahead and set this equal to 0. And this thing equals 0 when x plus 5 equals 0, or x minus 5 equals 0. Or, solving for x, I'm getting x equals negative 5 and x equals positive 5. So when x is -5 or +5, I'm going to get 0 in the denominator. So basically, this can't happen. So I'm going to go through and put not equal because that's actually what I don't want to plug in. If I plug in -5 or 5, I get 0 in the denominator, and that's undefined. So that's not part of the domain. Okay, let's try another example here. Now we're getting more exciting, but I'm not interested in the numerator. It's the denominator I'm interested in. All right, and I want to factor this denominator. Now, since this is a trinomial, I'm going to use the x method. So let me go ahead and draw my x. At the top of the x is going to be the first number, which is 1. A is 1 here, right? And the last number is -8. So that's going to be -8, 2 here. And I'm looking for two numbers that multiply to be -8, but add to be +2. That would be 4 and -2. Okay, now I'm going to show you a brand new shortcut for factoring. But this shortcut only works when a equals 1. And I'm referring to a being the first term here, where this is a is 1, b is 2, c is -8. And we talked about that when we discussed the x method. So when a equals 1, we can use this shortcut. So in this case, this is going to factor into these two numbers right here that we got when we did the x method. So this is going to factor into the denominator is here. I'm just going to rewrite the numerator, which is quite formidable. And in the denominator, we're going to get x plus 4 for the +4 and x minus 2 for the -2. So I'm literally taking these two numbers and I'm using the 4 and the -2 in the factored form. And it's factored. That's the answer. That's what it factors into. I don't have to go through the steps of grouping. But this only works when a equals 1. So I'm going to use this trick here in chapter 7 because we're going to do a lot of factoring and hopefully get you used to using this trick to kind of make our work a little bit shorter. But whenever a doesn't equal 1, we have to go the long way. So we'll see both types of examples. All right, so now I'm going to set that denominator equal to 0. Technically not equal to 0. And set the two pieces equal to 0, but technically not equal to 0. And solving them, I'm getting x can't be -4 or +2. I'm just going to skip showing the step of adding and subtracting because I feel like we're probably comfortable with that. And there we go. So those are the excluded values. All right, so let's move into evaluating rational expressions. So what that means when they say the word evaluating any algebraic expression, it means you're plugging in a given value for the variable. It sounds a lot easier. I'm sorry, it's a lot easier than it sounds. So let's look at this example here. Evaluate the following rational expression for when x equals -6. So they're literally telling me to plug in -6 everywhere I see x. So I'm going to plug it in here, here, and here. So that's going to end up being -6 squared minus 4 over -6 squared plus 6 times -6 plus 8. Okay, so -6 squared is +36 because negative times negative is a positive. And that's the same also in the denominator here. And then 6 times -6 is actually -36. And they usually put parentheses around that since it's negative plus 8. Okay, so these two terms actually cancel each other out, right? They add up to 0. And in the numerator, 36 minus 4 is 32. Divided by 8 is 4. So that would be the answer. And plugging in -6 is going to give me 4. That's what evaluating rational expression is. Okay, so let's get to the meat of the section, which is we're interested in reducing rational expressions. So we've kind of had some previous experience with this when you were working with exponent expressions, so things with just exponents in it, not polynomials, all right? So this would be an example of something you might have seen in a previous class. And if I wanted to reduce this, I'm literally going to kind of do it in pieces. I'm going to look at the numbers and then I'm going to look at the variables, but I'm going to do it individually. So I'm going to start with the m's and then look at the n's. All right. So let's start with the numbers. Most of us are pretty comfortable with reducing the 4 over 16. So we're dividing 4 into both of those terms. 4 goes into both 4 and 16, which means this is going to reduce to 1 over 4. All right. So I already know I've got 1/4. Now for the m's, we're going to, you might remember when you're dividing, you're subtracting the exponents. So m cubed minus m squared results in m to the 1. You don't have to put the 1. I'll rewrite this when I'm done. Okay, let's do the same thing for the n's. The n, now this n right here actually does have like a little 1 as its exponent. So when I'm subtracting those exponents, the 1 and the 5, that technically gives me a -4 if I just do 1 minus 5, right? -4. But another way of thinking of it is thinking of it as since the denominator has a higher exponent, that's where the result is going to end up being when we subtract. So when I subtract the 1 and the 5, I'm getting 4 on the n in the denominator. Another way of thinking of that is thinking of it as a multiplication. And this is kind of a useful tool. I could think of the n as being a single n in the numerator, and then there's 5 n's in the denominator, and they're all multiplied. That's what that means. And we could cross off one of the n's, and we're left with 4 n's in the denominator. That works for the m's as well. I could have done that. M cubed gives me 3 m's in the numerator here, and then m squared in the denominator. I could cross off 2 m's in both, and I'm left with a single m in the numerator. And it does work with the numbers, but we typically don't do it like this. I could think of 16 as 4 times 4, and I could reduce a 4, left with a 4 in the denominator. Okay, so the final answer is we typically don't write all the ones. We just write m over 4n to the 4th. Now, I kind of gave you several ways of thinking about this, but they all end up kind of getting us to the same basic answer. It's this approach, though, that I want to kind of emphasize because it's going to help us when we're looking at something more complicated. All right. So, what I want to note, and it's important for us to see, is that when we have a multiplication, we can just cross off things that are in common in the numerator and denominator. So, when everything is multiplied, like it is in this last example, we can simply cancel the common factors. Well, factor. There it is. The F word again. So what this means then is we want things to be a multiplication. So like, let's look at this first example here. This is definitely not a multiplication, okay? We're actually looking at a rational expression with polynomials here, okay? And they are not multiplied, they're subtracted. But I could make them into multiplications if I'm clever, if I can do any sort of factoring. And I can. In particular, in that denominator, I see that I could factor out a GCF of 3 for both of those terms. So I could rewrite this as 3 times x minus 5. Okay, now I want to notice x minus 5 is really close to 5 minus x, isn't it? So I could actually factor out a negative in that numerator. But I'm going to rewrite it with the x first because I want us to see that basically what we have in the numerator is exactly the opposite terms or signs, of what we have in the parentheses in the denominator, right? The x is a negative and the 5 is a positive. But in the denominator, the x is a positive and the 5 is a negative. So the exact opposite, which means that I could factor out a -1. And what that would do is change the signs. That's going to give me a positive x and a -5. Now, what I can do here then is cancel out the common factor of x minus 5. And I'm left with -1/3. All right, let's try that again. So here we have an even more complicated expression, but actually I can factor both the numerator and the denominator using techniques we've seen before. So in the numerator, I see I have a GCF of x. So I'm going to factor that out. And that leaves me with x squared minus 4. Okay, I'm not done because x squared minus 4, that's a difference of squares. That can factor again into x plus 2, x minus 2. All right. Now in the denominator, I'm going to need to use the x method. However, I can use my shortcut because a equals 1 here. So when I multiply a and c, that's going to give me 6 at the top of the x. Bottom of the x is -5. So two numbers that multiply to be +6, but add to be -5 are -2, -3. And it has to be -2, -3 because they both have to be negative in order to multiply to be +6. So that means this is going to factor into x minus 2 times x minus 3. I'm literally taking the -2 and the -3, and I'm rewriting it as the numbers here in the factors. All right. So now I see that I do have something in common in the numerator and the denominator. That is x minus 2. So I can cancel that out. And what I'm left with is x times x plus 2 and x minus 3 in the denominator. Now, you can leave this answer factored like this. You don't have to multiply the x in. In fact, most of the homework has you leave it factored. But just so you know, if you wanted to multiply the x in, it is the same thing. This is x squared plus 2x over x minus 3. It's the same answer, all right? But they don't typically write this as the final answer. They go ahead and leave it in this form. And they say that this is factored form because it's still written as a multiplication. All right, let's try one more. So for this one, in the numerator, I don't have a GCF. 9, right? It has 3, 25 is 5. Okay, but this is a difference of squares. So this is going to factor into 3x minus 5 because 3 squared is 9. 5 squared is 25. It's kind of a sad looking 5. Let me fix it. And 3x plus 5. Okay, in the denominator, to factor that, I'm going to have to use the x method. However, I actually don't get to use my shortcut this time because the a value here is 1. I'm sorry, is 3, not 1. So I can't use my shortcut. I'm going to have to go the long way. That's okay. Let's go the long way. So at the top of the x is going to be 3 times -10, which is -30. Bottom of the x is 1. So two numbers that multiply to be -30, but add to be 1. That would be +6, -5. All right, so let me go ahead and factor this thing then. So bringing down the 3x squared, rewriting it with the 6x minus 5x, and then I'll bring down the -10 and factor by grouping. All right, so out of the first group, I can factor out a 3x, and that leaves me with x plus 2. Second group, I could factor out a -5, and that leaves me with x plus 2. So my blob is x plus 2 times 3x minus 5. All right, so I'm going to write that up here. And there we go. I see the common factor. 3x minus 5. That's what they have in common. So I can cancel that. And I'm left with 3x plus 5 over x plus 2. And that would be my final answer.